Thank you. Hi. Today I'm going to today I'm going to be talking about an intro to GPU occlusion. In this talk, I will break down our adaptation of GPU-based occlusion culling using a hierarchical set buffer, and the results it has led to in our client's project. First, a quick intro. I am Leon Brands. I am a graphics programmer at Behavior, been so for the past year, and I've been in the industry for 3. Optimizations are my bread and butter. I spent years working on a multi-GPU ray tracing VR engine. And currently at Behavior, I'm squeezing out every tiny bit of performance to get our client's game ready for the Nintendo Switch release. Today, we're going to talk about why we integrated GPU occlusion, the concept or idea behind how it works, and then the practical application with a more in-depth breakdown of the math involved. Finally, I'll show you the impact it's had on the project, and we'll talk about some of the flaws with our current implementation. So why? Why bother with GPU-based occlusion culling? Why did we go through all of this effort, and why should you? The project with our client is co-dev. This means that we work side by side with our client as they are developing the game. And in our case, we are specifically responsible for porting the game to PlayStation, Xbox, and the Nintendo Switch. The game is run on all platforms, but it doesn't always hit performance targets. So a big part of my workload is optimizations. We have sort of limited control over the code base and no direct control over assets. The game itself heavily features user-generated content. Players can create and design their own levels using pre-authored chunks of assets. As a result, we can't easily do any form of baking. On top of that, the engine isn't designed with baking in mind, so there's no easy way to recognize objects as non-moving or static. Now, when I joined this project, I was presented with a challenge. We had a functioning port for the Nintendo Switch, but our GPU frame time was far above target. Now for the Nintendo Switch, you're going to be targeting a 30 FPS, which given some time away to the system, you're looking at 31 milliseconds of actual frame time that you can use. At the time, our GPU time ran around 42 milliseconds without any post-effects enabled. On top of that, our CPU time also could not maintain 30 milliseconds, and our memory budget was exceeded, which is the understatement of the year. So in short, we needed a miracle. We needed something that improves GPU performance without impacting the CPU and without increasing our memory usage, and without any form of baking or fundamental engine restructures. So here's the concept, which is largely built on the idea of reusing data is free. Now, in this case, we're going to be looking at the depth buffer. Of course, the depth buffer is already heavily used. We run a forward plus pass to reduce overdraw, and we also use the depth buffer to determine whether lights affect our geometry. But we can actually do more. Using the depth buffer of the previous frame, we can actually prevent trying to draw geometry in the first place. Now, how do you do this? The idea is to project objects as ABBs onto the screen, and if the ABB is further away in depth than all of the pixels in its area, we can consider it occluded. A concern with this approach would be the number of samples required to make sure the ABB is always visible when it should be. And we can't just check random points or the corners of the ABB, because if we don't check for every pixel in the area, we might not properly account for gaps in the occluding geometry. To solve that, we can generate a high set buffer, or a hierarchical set buffer. This is a depth buffer with runtime-generated MIPS. Each MIP bilinearly picks the largest, so the furthest depth value, instead of the average value. So what this means is that a single pixel at a higher MIP level will represent the furthest value in a larger area. For example, for a high set buffer of 1024 by 512, each pixel will represent the furthest value of 16 pixels, or rather 16 by 16. This means that with few samples, we can now get the furthest value in area, which is going to be perfect for comparing against the depth buffer with our ABBs. Now, to sort of showcase, this is the high set buffer as generated. You can see that it starts, as we go down the MIP chains, it will pick the further and further values until you're left with the skybox in the distance behind the windows. Now, how does this work out in practice? We'll start with a basic breakdown of our frames. Of course, ignoring countless other render passes that are not as relevant. So at the start of the frame, we collect our objects, which we then run into the depth prepass, after which we use the depth buffer generated by the depth prepass to generate our high set buffer, which can then be used by occlusion culling. And then we run our lighting pass or our base pass, followed by post effects, after which the frame is presented. Starting at the start of the frame, we sort of introduce a problem. The occlusion culling uses the depth buffer of the early depth pass, but the early depth pass is also one of the places where we can gain the most by using occlusion culling. So instead, we use the previous frame's results. Now, the occlusion culling pass of the previous frame has given us a buffer of U and 8s, indicating with a 0 or 1 whether the object is visible, and the rest of the numbers we use for error codes. Before we can use this data, we do need to quickly wait on a fence to make sure it's ready, which was signaled after the previous occlusion culling pass. Then, when we're collecting objects for rendering, we skip any objects that are already out of our frustum or out of our view distance, after which each object gets assigned an ID. Now, each object has an array of 2 IDs, 1 per frame. One is used in the current frame to read from, and the other is used in the current frame to write to. And then they sort of alternate. Internally, the occlusion create ID function here uses an atomic counter, which effectively results in an index into the occlusion input and output. Then, using the ID, we store the ABB, which is a world space ABB that fully encapsulates our object. After that, we can use the occlusion results from the previous frame using the other ID to check if we should be rendering the object. And if this returns false, we simply do not render it. After we've collected all of our visible objects, we can render them assured that we have minimized the number of objects that we actually need to draw. The depth-only prepass is very straightforward. It draws all the visible objects and generates a depth buffer, which will look something like this. After which we can use the depth buffer to generate the high set buffer. Now, for the purposes of map generation, the high set buffer's MIP 0 is always aligned to the nearest power of 2 downwards. So for example, on a 1080p screen, our high set buffer is 1024 by 512, which we find is more than enough detail for our use case. In the worst case, we're sort of being a bit more lenient for small objects. Then, using the depth buffer, we can generate the high set buffer. This is done in a very simple shader pass, where we iterate over each MIP, taking the previous MIP as the input and writing to the current MIP. All the while using a bilinear gather, where we return the maximum value that we find, which you can see here is incredibly simple, and just a couple lines of shader code. Finally, we prepare our occlusion culling pass. We upload all of the ABBs that we've previously gathered in the frustum culling pass. And we fill the result vector with error codes, we bind the shader's resources, and we dispatch our compute. Now, before we get into the intricacies of the compute shader, which is arguably the most interesting part, I want to take a moment to cover some of our efforts to keep this technique as stable as possible. When I first inherited this technique, there had already been previous attempts at implementing it, and it was incredibly broken and unstable. So on the next slide, I'm going to cover a couple of things that I've done to make sure that this technique remains stable, and I think they're worth mentioning. So, as I mentioned, we are working with 2 IDs per object, which get alternated between frames. And with data running across frames, objects going in and out of frustum, etc., it is incredibly important to be vigilant about clearing the object's IDs. So whenever we read out an object, we clear it so that the next frame can't accidentally use it. If an object is not rendered, we also clear its ID just in case, etc. And then finally, if anything goes wrong, it doesn't, because visual stability is key. So we'd much rather give up a little bit of performance on an uncertainty than have an object visually disappear or reappear on screen. So if we can't find data, if an object doesn't have an ID, or if our occlusion calling pass from the previous frame somehow isn't ready yet, we just pretend like stuff is visible, because that is a lot easier than dealing with visual artifacts. Now, for our GPU implementation. On the compute side of things, we're going to start with a pretty simple setup. We have a structured buffer containing our ABBs, a texture-to-D for our high-set buffer with all of its MIPS, and a read-write buffer with uint8s that we write our results to. Finally, we have some constants to help us along the way. Each thread handles a single item and is expected to write a result into the results vector, or buffer. If there's no result, we write some form of error code. Each thread fetches an item from the items buffer using the thread index. Using that, we can compute the ABB size, and then use that to calculate each corner of the ABB. Each corner is then passed into a function, which transforms the corner's position into 0 to 1 screen space. After that, the function outputs the closest z value and the minimum and maximum xy values. Using this data, we can compute a UV space square, which we can use to sample the depth buffer, which is shown in the image below, and we'll end up with the square on the far right. So using the square, we effectively have the smallest shape encompassing square in 0 to 1 UV space. So our next goal will be to figure out a MIP level on our high set buffer in which our square can be depth tested accurately with the least number of samples necessary. For this, we'll be using a point sampler because we care about the precise values of the depth buffer, which does also mean that if our square covers multiple pixels, all of those pixels need to be sampled. To match those requirements, we're going to be computing a MIP level in which our square can be represented by 1 sample per corner. This means that each sample needs to cover at least a half square size. Now, we can compute a matching MIP level by converting the square size to pixels and taking the log base 2 of its largest dimension. This lets us calculate how many times we need to divide the square by 2 before it fits in a 2 by 2 square, which is pretty much exactly what our MIP levels also do. So for example, in this example, our square is 0.01 by 0.05, which means that its largest dimension is roughly 10 pixels. The log base 2 of that is 3.3 something, which after rounding up results in 4, which is going to result in the MIP here on the right. Now, the question on your mind is going to be, is that the correct MIP? So let's find out. Our high set buffer for 1920 by 1080 starts at 1024 by 512. So let's say our square is an imaginary model we want to draw here, in front of the plant, just behind, in front of the plant, but behind the chair, with the image on the right, sort of as reference, because these HZB levels get less and less visual as you go on. So the first question is, why can't we go to a more detailed MIP and potentially include more objects? Now, if we were to go to MIP 3, each sample would cover 8 by 8, meaning that if those samples were to be sampled at the corners, our 10 pixel wide square would have a couple pixels left in the center, which would be unsampled. For example, in this case, the corners of the square have all sampled a part of the chair, and thus we would consider this square to be occluded, even though it should be visible because there is a gap between those chair parts. So in general, sampling at too low of a MIP level might mean that we don't appropriately account for gaps in geometry. In this case, the chair, but in general, it will cause objects to be occluded when they shouldn't, which is incredibly apparent, especially when you move your camera around and objects sort of go in and out of existence when moving. Now, at MIP4, the MIP that we calculated, the high-set buffer has a resolution of 64 by 32, meaning that each pixel represents an area of 16 by 16. As you can see at this level, the high-set buffer is going to start ignoring the chair spots because any sample in this at this level might also be visible through the gaps. The pot's depth remains, which we've established our squares in front of, meaning that in this case, our ABB will be properly visible. Now, if we were to go to MIP5, we would cover a larger area than necessary. In this case, with our square, it doesn't affect us negatively. The area is still covered by the plant pot, and we'd be in front of it anyway. But if our square would have been behind the pot, but near the edge of it, it might have been considered visible where it didn't need to be, causing a false positive. Now, taking too high of a MIP level isn't the worst thing ever, but the more accurate we can be, the fewer objects will render. Then, using our computed MIP level, we can sample the square's corners. We'll use the previous computed min and max to determine the exact sample points. And then using the full depth samples from those corners, we can take the largest value, representing the furthest pixel in that area. So then, if our ABB's closest that value is further than the furthest pixel we found in its depth buffer area, we can confidently say that the ABB is occluded. Of course, in our actual code, that last part looks a little bit more like this, but that's less nice to explain. We do also add a small bias in favor of very thin meshes, such as decals, which technically are meshes. But so let's talk about what all of this work resulted in. Flaws. Let's quickly go over some of the flaws that we've noticed. So as discussed before, the occlusion culling pass uses results from the previous frame so that it's available before the early depth pass. This sometimes means that objects can pop into existence when they shouldn't. This is especially apparent if, for example, you move a camera through a wall or very strongly parallel along a wall. We do find that it isn't very noticeable, especially at higher frame rates, and even in the cases where it's noticeable, we've considered it to be acceptable for our use case. Other than that, the occlusion culling approach can also result in false positives, particularly with large ABBs. When a large ABB exceeds our NDC space, the best thing we can do is clamp it to our 0 to 1 space and sample our depth buffer. But that might not always be representative of what's actually seen on screen. For example, if you were to imagine a very large water towel under the camera, it might exceed behind the camera, in which case the closest corner is going to be 0, which is always going to be in front of all other geometry, even if the water isn't necessarily in front of other geometry. In the worst case scenario, this results in a false positive, so an object might be visible when it shouldn't, which isn't the end of the world. Now, for the actual results, on the Nintendo Switch, the occlusion culling pass took just 0.03 milliseconds, where it saved us a total of 4.8 milliseconds. The exact numbers, of course, differ depending on the scene, the area you're looking at, etc., but always result in a positive impact. All our other platforms also benefit from this technique. For example, on the PlayStation 5, we've gained a total of 1.9 milliseconds. And on the PC, even on higher end PCs, we gain a total of 1.8 milliseconds. Thanks to the flexible design, that I've described here, we've also been able to extend this beyond just meshes. So the occlusion culling path also runs for particle systems, foliage, fog volumes, and water planes, which sometimes are less effective, but they were released bad. And with that, I am sure I haven't covered my time, so are there any questions?
Thank you, Leon. There's enough room for questions, so please. There are already multiple questions.
Do we third?
A nice cube you can throw.
Okay, so I barely understood what you were explaining, because this is not my Richting, but I do have to ask, is there ever a scenario where that type of occlusion culling was more expensive than just not doing it at all?
We haven't ran into that at all. As I've described, it's like 0.03 milliseconds, so you're at a very low cost basis. In our case, we're looking at our game is very very narrow rooms and like ongoing rooms afterwards, which are usually not visible. So in our case, it's incredibly beneficial. I can imagine that in a larger open world game, you might have less of a benefit. Mileage might vary.
Okay, thank you.
Another question up there.
Hi, thank you. Great talk.
Thank you.
Have you considered or experimented with more samples than just the four corners of that square so that you can sample at a lower MIP level and get more accurate culling?
We have not. That could be a consideration. Yeah. Haven't tried. Haven't found a need so far, but who knows? Maybe being more accurate could help.
Well, maybe you get some more time now to improve it.
Since I have the thing, very nice talk, very well presented, very clear. You mentioned it was GPU cooling. Did you? I mean, given your background doing software rendering, did you ever think about trying it on the CPU? You said you didn't have CPU cycles. Were there other approaches not on the GPU?
Yeah, so in this case, we really need something that didn't affect our CPU time as well. Since even now, after all of this, our CPU time still struggling. This just turned out to be sort of the holy grail, where we didn't have any real cost, but incredible benefit.
Great. Some additional questions up there.
To get rid of that one frame delay where actually you're using an old Z buffer, could you use temporal reprojection to at least get partly rid of that problem?
Potentially. Currently, since we're currently still relying on GPU to CPU interrupt, with all the data being copied back to the CPU, we can't really afford waiting for a pass, since that would significantly reduce the sort of parallelism of our frame. But in the future, we are going to be looking into indirect draw, where we might be able to do the GPU occlusion just before the draw. In which case we would try to temporarily reproject. I can imagine, since you're still using the depth buffer of the previous frame, we might still run into some issues where, especially if you move through a wall, you have a very rapid change in depth buffer, where you might not be able to make up for it.
But at least if the camera moves smoothly and there's no jumps, then it might help a bit.
Yeah.
See, thank you.
Great. Another question here. You can use this one.
Thank you. Yeah, I don't get the thing on my head. Thanks for the talk. It was really, really interesting and inspiring. One thing I'm wondering, though, is if you would have had more freedom to change things in either the engine or the renderer, what would you have done differently?
That's a good question. I think if we had more freedom, we might have we might have designed like changed the engine in such a way that we could maybe identify objects as static, and then we could use a more traditional sort of CPU-based hierarchical occlusion calling pass. But in this case, this was sort of minimally intrusive.
It seems like this method would also be easily portable.
Certainly, yeah.
Thanks.
Yeah, and the shader passes that I've shown are incredibly simple. There's no special tricks going on. We have it working on all platforms and wouldn't take long to take over to anywhere else.
Great. Some more questions? I guess that's it. It's also a great start. I think you've been there for a year now.
Yeah.
It's great that you can introduce this and actually made it. So congrats on that. And thank you for this great talk. So another round of applause.